Good. So actually, this is a brand new talk. It's kind of so you guys are guinea pigs. It's a dry run for a talk I'm giving to I'm giving a stock workshop to a group of theory folks. Anyway, so talking about approximation guarantees for data-driven algorithm design. It's based on a paper with Vaidehi Srinivas, Northwestern, and also thoughts based on a course that co-taught with Ravi Sharma in the fall on generally the topic of data-driven algorithms. Okay, so data-driven algorithm design. So if you want an algorithm to do particularly well on problem instances coming from some domain, it makes sense to try to train it or tune it on typical instances from that domain. So maybe you can solve matching problems coming up in a particular resource allocation domain, or clustering problem coming up in a particular application area, news articles by topic, or maybe some planning or scheduling or logistics problem, So that's actually, what companies implementing algorithms actually do. Theoretically, we tend to analyze algorithms based on either worst case or particular distributional models, but can we analyze this kind of thing theoretically? So this brings up the question of giving theoretical guarantees for this sort of data-driven algorithm design. This is a direction actually led by Nina Balka and her group. She talked a little bit about this on Monday, mostly about some other things, but she mentioned a little bit at the end. It's a lot of work, and generally the high-level picture here is you define a parameterized family of algorithms, typically motivated by one or more algorithms, either with good worst-case guarantees or good empirical performance. And then you might say, well, at least this family contains at least one algorithm we know something about, whether it's empirical or worst-case bounds, but maybe it's a natural class of things, and then we can try to tune that based on data. And then what you might do is given a sample of typical problem instances, maybe you might model that as IID draws for distribution, try to learn a good setting of the parameters that you hope is going to then do well in the future. And what comes up here is there are challenging statistical and generalization questions, because often the behavior of an algorithm can be a highly discontinuous function of parameters. For instance, if you're doing some clustering thing that kind of groups things, you make some little change and what your distance function is, and all of a sudden you group this way rather than that way, and the whole rest of the algorithm changes too, for instance, or something like that. So it can be kind of interesting, theoretically, and a little tricky to analyze these things in terms of sample complexity. If they're challenging algorithmic questions, how do you algorithmically, that seems to be the harder part here to try to get to a theory for us, the algorithmic problem of finding these good parameters. And you can also aim for online regret guarantees where you don't make distributional assumptions. You want to have good performance in the sequence. And again, there's challenging analytical and algorithmic questions. Okay, so actually to learn more, I taught a course on this with Ravi Sharma. The best way to learn something is to teach the class on it. Those are my notes. Our notes of Ravi's and mine together. Okay. Okay, so approximation algorithms for this. So the idea that I want to talk about is trying to use ideas from approximation algorithms and competitive analysis, which is kind of the same thing in an online framework, to try to simplify the algorithmic challenge of trying to find, the best settings, by allowing ourselves to, be off by some factors. Maybe even make it easier to compare to stronger benchmarks, and we'll see that. By sort of willingly giving up some constant or logarithmic or polynomial factors in what we're doing. So for a lot more on approximation algorithms, you can take this course. And we're going to focus, I'm going to focus in this talk on what our results were on, which is on warm start initialization, which is a particularly well-behaved setting for this. There's a lot of different settings, and this I'll say a little more, but this is basically a setting where the way the family of algorithms is kind of defined by where you start them from, and that's what you're trying to learn. So I'll get back to that. It's particularly well-behaved for things like this. We'll see a cameo appearance of the K-server problem. This will mean something to you if you were doing algorithms research in the 1990s. All right. And I just to note, we are going to be losing multiplicative factors relative to our benchmark. So the perspective or hope here is the thing we're competing with, the optimal, initialization strategy, hindsight, is asymptotically significantly better than a generic start. So if we're within a factor of 3 or something, or even log n or whatever, or something, we're going to imagine that the optimal is so asymptotically significantly better than otherwise. So we're okay with losing, putting a big O around things and so forth. All right. So here's the setup. Many algorithms run faster if you initialize them with a solution that is close to the right answer, close to what you're looking for. And there's a number of cases. Ford, Fulkerson, Max-Flow algorithm, classic algorithm for midway perfect matching. I could think of gradient descent. If you start close, there's fewer steps to take. Depends what you mean by close, and other things, so forth. Okay, so this is the setting, and kind of we can think about this as having some sort of metric space on solutions where we can just define the distance. Okay, and I'm going to be assuming it's symmetric, even though it doesn't have to be in the real world. It might not be, but for the talk, let's pretend symmetric. Where the distance from S1 to S2 represents the cost if you start from solution S1 and then solve a problem instance I whose true solution is S2. So if you start close, it'll take fewer steps to get there. That's what we're going to. In fact, the definition of distance is how long is it going to take. That's our distance metric. In reality, two things. One is it takes time to check a correct solution even if one's handed to you. So the distance of S in itself shouldn't be 0. It should be greater than 0. That actually doesn't affect anything. That's if you want. In fact, it only makes our problem harder if it's 0. If it's greater than 0, you can kind of pad things with, and it reaches as a name. No, don't worry about that part. What we will assume it's symmetric, and that's one thing which is maybe you could argue against that, and then our results really do require symmetry. Okay. Okay, but so there's so think about, we have an algorithm. If we start close to the solution that we're hoping for, we don't know where that solution is, but if we start close, our algorithm goes faster, and we define the definition of distance is how much time, how much cost is it going to take if we start from one point and the actual solution is another. Okay, so that's what we think.
And you are assuming there's a notion of correctness. You've got a checker that's going to tell you whether this is a solution.
Yeah, so right. So our algorithm is for solving some problem, and let's put that into the algorithm. There's an algorithm for solving a problem. You started off with some initial state, maybe L zeros or maybe something else. It runs for a while and then stops and hands you a solution.
But I'm thinking something like Lloyd's algorithm. It's an optimization problem, right? So there's no notion of solution. There's just score.
Okay, so let's think about running time as a thing we're looking at here. Right. With Lloyd's algorithm is the quality of the solution, and then right. And where you start might end up with completely better or worse solutions. So, but let's think about something where the algorithm, like always, is correct. In the end, it'll output the right answer. Just how long it takes is going to depend on where you start. I think that's the cleanest thing to think about here. Yeah, good. Yeah.
Should we think about the distance as some sort of upper bound of the running time? Because it depends on the specific instance.
Let's think about it as exact for this.
If it doesn't depend on I.
Yeah, right. It just depends on the solution. So I'm kind of going to be thinking about it as exact. If it's an upper bound, then the thing we compete with, we're going to be competing with this upper bound. So in other words, we'll have something that has some cost in terms of distances. We're going to claim it's within a factor of 3 of some optimal. And it might be, well, actually optimal did much better because for some reason optimal paid a lot less. But right. So if we want to think in terms of just being an upper bound, the thing we're competing with is this upper bound. So that's
what would be some examples of combinatorial problems that admit this distance structure and symmetry?
So the Ford-Fulkerson one is one example that works pretty well. That you can start from something that's not even a legal flow, and it's the distance between two flows is just you go over the edges how much flow, and so there are, in fact, there are several results. So let me get to let me get back to that.
Sure.
So one way to think about this is that running the algorithm from a starting point is like growing a ball around it. You don't know where you're trying to get to, but you're growing this ball, and at some point the solution, you find it. So that's kind of a way to think about it. So growing a ball. Okay, so what's known? So there's been recent work on learning good initializations for a distribution of instances, and so these papers. So on faster matching field or duals and predictive flows for faster Ford-Fulkerson. So they do two things. One is they show that the algorithm indeed has this property, and then they look at this. So there's this related area of algorithms with predictions where kind of the idea is you want to design an algorithm that will do well if you have a good prediction. And then here, we're assuming you have an algorithm that will do well if you have a good prediction. The question is, what do you predict? So sometimes it takes work to get an algorithm that has this property. And then there's also work on competing with the best single initialization for an adversarial sequence. So that's what friends call learning predictions for algorithms with predictions. Okay. So one thing maybe to motivate some of this is, what if the best single initialization is not good enough? Right, if we're willing to lose some multiplicative factors, maybe we compete against some stronger benchmarks. So what I want to talk about today, so two results in this direction. One is trying to learn a mapping from features of the instance to a type, where what the type here just means, say, one of the k types, where it just tells you which initialization we're going to use. So we're going to try to do two things. We're going to find some initializations, these red dots, then learn a mapping that goes from the instance to which red dot should you start with. So something like that. Okay, so think of that's going to be the kind of problem. And the second one is an online algorithm for trying to compete with the best adaptive sequence of worm starts, where these things are competing with something where these might move around. Maybe you start with some instances over here, and then you move to instances where the solutions are over here, and then over there. Maybe it starts bouncing back in some way, or who knows. But maybe it's not a distribution. Okay, so I'm going to talk a little about each. All right. So, learning on mapping. So let's assume we have a probability distribution over instances. Then the natural thing we can do is we take a bunch of them, we solve them, those are the blue dots, and then pick a k, like 3. What would be the best 3 initializations that, if we could kind of magically guess which one to use for each instance, that would be what's called the k-median problem. K-median problem is find k, we call them centers, that minimize the sum of the distances from each point to its nearest center. So we could kind of magically guess which one would be the right center to use. That distance, how much we would pay. Okay, so if we could do that, then we could say, okay, here's a classic algorithmic problem. Sure, it's hard when k is function k, for small k, but it's hard, it kind of depends on the model. But yeah, just draw a sample, we could analyze that sample size, find our solutions, solve the k-median problem on our training sample, do some generalization analysis to say with high probability that it'll do well on new data coming from the same distribution, right? That would be a sort of natural learning theory way to do this. Okay. But actually that missing one thing. Okay, so here's like instance-based solutions. One issue is that the initializations that we want to use depends on the mapping we can find. So the k-median problem would be that k-median problem solution would be the right answer if we can actually map all of these guys. I think this is 1, 2, 3. We can actually map all of these guys to 1, these guys to 2, and these guys to 3. We need our mapping to take each instance and map it to the right one. And we might not be able to do that. Okay. There. Right. So it could be that, that we can't find this one, that all we can do is find that one. And if that's the one we're finding, where these are, those are the regions, 1, 2, 3, then those red dots wouldn't be the best starts to use if that's the mapping. If that's the mapping we're using, then we would want to use maybe red dots starts to look like this. And so that's confusing because the starts we want to use depend on the mapping we find, and so we have to kind of maybe find them together. Of course, the first mapping is better. I mean, the mapping that looks like this, that would be the best mapping to use. But maybe we can't do that. So what I mean is, all right, given the instance, we don't know where its solution's going to go. We could figure it out by actually solving it, but that would be overkill. If you're actually solving the instance to figure out which worm start to use, then that's a bad idea, right? Because the mapping has to be something fast, like how many edges are in the graph, or just some quick thing that's going to, is it a lot, is it a medium, is it a little? That's going to be your which start to use, some simple function. So think of this family of mappings, some simple kinds of things, and it might not contain the perfect. So the small issue that I'm going to talk about is just this question of, do we need to solve for a pair simultaneously, mapping and centers to use? Or can we just do a two-step thing? First, solve a problem that we know, it's a K-median problem, find solutions, fix that. And then once we fix that, now solve for a mapping that minimizes a well-defined loss function, where the loss function is, for this guy here, this is the loss for assigning it to type, say this is 1, and that's 2, and that's 3. If you assign a type 1, you get this loss. You assign type 2, you get that loss. You assign type 3, you get that loss, right? So there's a well-defined, if you can solve for the centers first, now for every instance there's a well-defined loss, and we can see we could do the thing we're more used to, which is try to solve for a function in our family that minimizes empirical loss from something that because the question makes sense here. So it'd be nice if we could do them one at a time and not try to do the simultaneous thing of finding the function and the centers together. And so that's the question that kind of look at. Oh, I think so. Oh, okay. Right, so here's the question. Imagine we have an ERM oracle for our family that you give it a loss, well-defined loss function. We'll go ahead and optimize for you. Can we, if we optimistically just solve the K-median problem first, hoping that we'll be able to find something that's close to what we really want? Get some centers, call them C1 through CK, then find the mapping of lowest loss with respect to these centers. So the loss is the sum over all your instances of your training set of the distance between the starting point that your H tells you and the actual solution that you're going to find of that instance. So that's what you want to make. Okay, so suppose you do that. So it turns out that's within a constant factor of 3 of the best pair of function and center. Okay, so that's just an example of a kind of approximation, right? So if you first find centers and then find the function that has lowest loss with respect to those centers that you found optimistically, does it make sense? This formula here, this formula is just the sum over all your instances of your training set of how far was the actual solution instance to the starting point that your H set, and you just add those up. And that's the thing you minimize. Anyway, the claim is it's within a factor of 3. So we can kind of separate. Okay, so maybe this is the thing we find that minimizes within our family for these centers, and with these guys all going to 1, these guys going to 2, and these going to 3. And yeah, of course, it would be nice if we actually split them the right way, but we weren't able to do that.
Okay. So here, are you assuming that we have direct access to this distance function, or we need some compute actually?
Oh, so I'm imagining this is our training set, so we can go ahead and solve, for these. Yeah, and then we can then figure out the distances on our training set. It's a good question of, in this whole space. So with another constant factor, you can kind of assume that the starts are always solutions, previous solutions. So we can just think of it as a matrix among the solutions themselves. Just for every pair of solutions, how far would they? So that's a good question. But you could imagine, okay, where are these centers supposed to live? What does this metric space look like anyway? Right. But you could just imagine, think of them as previous solutions. Yeah. And then you can resolve for the centers if you want. We just can't prove it. The technical assumption, okay, so the answer is yes. If you could do this, you get within a factor of 3 under a technical assumption, which is just that your family of mappings is such that it doesn't really matter the numbers. If you have a function that can map this to 1, this to 2, and this to 3, you can also map this to 1, this to 2, this to 3, both of these to 1, this to 2. You can, the actual numbers, and you can map everything to 1 if you want to. Okay, if you can partition the space this way, you can label that. Okay, and the analysis is just a few triangle inequalities. You can sort of imagine there's some triangle inequalities. I will actually show you some of them, but it's not important. It's just there's some triangle inequalities. But just to show you roughly what the analysis looks like, you can say, well, look, we first fixed these centers, the C's, and we found an H that was ERM gave us, and so it's optimal for those centers. So that's at least as good as the H star was for the center. H star is optimal for its own centers. That's the best pair. H star, C star is the best pair, function and centers. We first found some centers, C, not the C star. We optimized for that C, that's our H. Because we optimized, we're doing at least as good as the H star would have done on our centers, because we could have found H star. In fact, the best fine proposed with H star was just renumbering for those centers. Okay, fine. So we just need to find that. So maybe this is the H star. So we need to add up those costs. So to add up those costs, like here's some point with some center, some solution. Here is the H star's cost, phi on H star's cost. So we have to add up this distance here. And that distance, we can say, well, that's the most of the cost to first go to H star center, and then from H star center go to the solution. Okay, fine. This second green line, this green line here, that's nice because that's H star's cost. That's how much H star was paying anyway. So that's 1. I said we have 3 to work with. 3 times the cost of H star, and one of them we already get from here. That's 1. We just need to bound this part, which is the distances between these centers and these centers. And that you can do with another one that basically you can say, look, we defined, I didn't tell you, but we defined like this map because this was the closest center to this guy. So, so this, if we pick actually the center that this one really was supposed to use and the optimal, and the unconstrained optimal solution, if we could just came median, if we didn't have to partition in any particular way, we'd really like to use this one. So let's look at that. This is only longer than this one. And this distance is about this plus that. And so there's another cost of H star plus the cost of the unconstrained optimal. So those are just the triangle. So you end up saying it's the most the unconstrained optimal plus twice the H star. The details are not important. Just want to say that if with this approximation perspective, we can then simplify the learning problem to kind of a standard ERM type learning problem, rather than a kind of confusing learning problem of trying to learn a good mapping and a sentence. Okay. All right, that's part one. Summary. So if we're willing to lose some constant factors, we can first solve or possibly solve a classic optimization problem, then reduce to a standard ERM with a constant. So again, what I'm trying to do with these examples is as I said, it's to show that there are, I think, from someone working in approximation algorithms, there are interesting kind of algorithmic questions that I think you can get by taking these problems, saying, hey, if we're willing to lose some constant factors, maybe we can simplify what seem to be pretty hard algorithmic optimization problems to prove things about. Maybe we can prove things about them by losing some factors. Here we're proving something up to an ERM oracle. This part is, chances are, and be hard like it always is, but at least, we're solving something up to at least something we understand. We agree we can do it even if it's hard. So that's okay. Yeah.
You mentioned that this function is symmetric, but I don't know higher stage, right?
We are in some places using the distance because we're going one way and the other. So we say it's triangle inequalities, but sometimes we're going from the start to the solution, sometimes from the solution to the start. Okay, so now let me switch to online adaptive initialization. So what if our instances are not IID? Can we compete with the best adaptive initialization? Or something more confusing I'll get to in a second, which is a set of K adaptive initialization. So what do I mean by the best adaptive initialization? Well, first of all, for this to make sense, we need to charge our offline competitor for movement. Otherwise, the optimal way to adaptively initialize is to guess the solution of the problem you're going to solve next and use that for the problem you're going to solve next. And that would always pay zero, but it's not, that's just not a reasonable benchmark. So the benchmark is the best way you could, for instance, pick a center, let's say this one, pay to solve that problem, then pay to solve that problem, then pay to solve this problem, pay to solve this problem, then move over to here, and then pay to solve that problem, and that problem, and that problem, and that problem. So you have to pay to move your center, and you have to pay to solve your problems. So in hindsight, what would have been the cheapest way to move the center around, solving for you have to pay for moving the center and solving the problem. Does that make sense? So does the example I gave make sense? So in other words, you pick a start, you have to pay to solve, and then you pay to move. Okay, so that seems like a reasonable benchmark. So for K equals 1, it's the optimal distance of the first start to the first solution, plus we can now move the center if we want to. Here we didn't. We can solve the second problem. We can move the center if we want to. We chose not to. We can do it again. We can do it again. At some point, we chose to move the center, and so forth. So we look back in hindsight and say, what would have been the best thing to do? Yep. Okay. All right. And we're going to consider the case now where there's no feature information, so there's no mapping. It's just all we have are the points. Okay. It'd be interesting to kind of connect these. Okay. So some examples, like the scenario we just looked at, is pretty good for having a single solution that we move. We sit on the left for a while, then we move it over to the right for a while. If, on the other hand, our solutions bounce back and forth between these two kinds, then this would be good for the K equals 2 case, where we're going to imagine we have two solutions that we can use the closest of whichever of them, and we can move them. So the thing we're competing with is the best, in hindsight, way to have two solutions, where each time something comes in, your two warm starts, anytime something comes in, it uses whichever one is closest, and then it's allowed to move them as it likes. it's a pretty strong benchmark, right? Because you're like, how are we supposed to know where are these? But this would be good because then we don't want to bounce back and forth, but then we can just set these two dots and leave. So the first claim is that so if you want to actually so competing against the best adaptive thing. So I guess maybe one more point is that in both of these examples, these are much better than the best fixed start that you can't move. So in both cases, this one and this one, if you had to pick a start you couldn't move it, then maybe you pick something in between, and you're going to not be doing so great. So it's really nice to be able to move that start. Okay. And claim is simple factor of 2 approximation for the case of competing with the best single moving thing. And the simple approximation is just use the solution to your previous instance as the warm start for your next instance. Right? If you use the solution to the previous instance as a warm start for your next instance, then you're going to pay this green line. Let's imagine S1 is actually not an instance at all. That's your generic initial start. So S1 is the generic initial start of your algorithm. S2 is actually the solution of your first instance. I should have subtracted 1 in all these numbers. Okay. But then we just use that, and then we have to pay the green, sequence, which is just we use the solution of the previous instance as the warm start for the next one. And if we want to compare to the best adaptive sequence, so it's actually, not too bad because, our cost is this sort of green line, and that's at most what you get by, in other words, instead of going from S1 to S2, you can go from S1 to the center that the optimal solution was using, move this optimal center if it was using to, move to the next solution, move back, and so forth, right? So again, everything's triangle inequality here, I guess. But right, so just so instead of paying the green thing, you always pay more by going to the optimal, whatever the optimal thing was, and going to the next one, back to where the optimal was, next one, back to the optimal one, and over here. You're paying for following the optimal along and going along. So if you do that, just, that's at most, 2 times the amount the optimal one is paying, because if for every edge there on the optimal cost, you have to go maybe there and that. That's all right. Just like kind of the TSP, there's paying tree kind of thing, right? You got to follow each other and that. And so you're just doubling everything. And so it's at most 2 times the cost of the optimal sequence. So to factor of 2, just using the solution to the last instance for the next problem works great compared to this. So that's this. Okay, now what about approximating the best set of K adaptive initialization? So we want to compare with having, in hindsight, K points that can move around. That gets more confusing. Okay, so what I'm just going to sketch out is a few ideas here. So one, if we knew that each new problem instance was likely to have a solution year 1 of K possible starts, and we knew the K starts, we just didn't know which one of these we should use. So somehow we magically know the next solution, the next problem instance is close to one of these solutions. We just don't know which one. And one thing we can do is run K copies of our algorithm in parallel. So we'll pay K times too much by doing a little bit from here, then a little bit from here, a little bit from there, and you'll just start growing out these little balls, and you keep growing and growing and growing until finally one of them, these K copies, one of them solves the problem, and you're done. You just pay K times more. But if K is small, we're thinking 2 or 3 or some small number, that's just our conjugate, a small factor. And so that's worth it. A lot better than jumping around. It's just in parallel. So that's one thing. If we knew that. Of course, we don't know what they are. This would be within a factor of K. Right. Of course, we don't know the locations of these. They're convenient and they're moving over time, so that's a problem. Okay. Second idea. With only constant factor loss, we can assume the warm starts we're competing with are solutions of previously seen entities. This the question was asked earlier. So we can, by triangle inequality, similar to the one case, we don't know where those solutions are, but at least we know that they are solutions of previously seen instances. They're not some crazy other thing up to a constant factor. So that's just okay. So that's helpful. So maybe the optimal hindsight thing to have done is we start with these two solutions, that'll be the solution to the first two problems. Solution to problem 3 comes along, we use solution 1. Then problem 4 comes along, we use the thing that was in solution 2. Problem 5 comes along, we use the thing that was in solution 3. Problem 6 comes along, we use the thing in solution 4. Problem 7 comes along, we use the thing in solution 6, and so on. Maybe that's what we should have done. Of course, one problem is we don't know which are the currently active ones. If we knew it was the most recent two solutions, that would be, we would know. But it might not be the most recent two. In this case, it's 5 and 7, where these are not 6 and 7. But they could be different ones. We just don't know which two are which K. So that's a problem. In fact, okay, so this again, for those of you active in algorithms in the 1990s, this is a lot like the classic K-server problem. In the K-server problem, you have K red dots called servers, and you have requests that are coming, and you need to move servers to satisfy the request. And this is exactly the thing you're competing with in the K-server problem. In fact, it's very similar. The differences are, in one sense, it's harder because we don't know the location of the new point we're trying to serve. Normally, the K-server problem, you know where you're trying to get to, so you know which one to move, sort of. You don't really know which one to move, but at least you know where you're trying to get to. Here, all we can do is grow balls. Also, on the other hand, it's easier because we aren't limited to using exactly K warm starts ourselves. It's just the thing we're competing with. Our algorithm can do whatever it wants. We're just trying to compete with the best solution, which is K warm starts. So that can make it easier. It's also different because ideally, we like to get a simultaneous guarantee, namely that simultaneously for all values of K, our cost is less or equal to the minimum out of all values of K of our approximation ratio, called G of K, times the cost of the best set of K adaptive initializations. So it turns out that having just one adaptive initialization is good enough, and we'll do really well compared to that. If you really needed 2, we'll do a little bit worse compared to that. If you needed 3 to do well, then we'll do worse times that. We like to have a single algorithm that kind of doesn't need to know this K. So that would be nice. So that's also good. Okay. So, third idea, I'm going to get to several ideas that this one doesn't work, but okay, but it's going to help. One idea is start on all previously seen solutions, just run in parallel from every solution we've seen so far. But one of them is where the thing we're competing with is going to be used in. The problem is that this is going to slow down as we see more stuff because we're parallelizing over more and more and more things, and so our approximation ratio is going to degrade. It's going to increase with the number of instances. We've seen, 10 instances, then we'll be growing these balls at a rate of 1 over n each one because we're parallelizing over n things. That's too many. All right. So how about favoring more recent solutions? Let's just put 1 over I squared, I log I squared, so something that sums up to a constant fraction of time on the more recent solutions. And that kind of makes sense to do, actually, because if you think about it, most of the time, the optimal trajectories we're competing with, most of the time they have to use a fairly recent solution. Why? Because whatever solution they use gets updated to the most recent solution. Wait, sure, it doesn't have to do that. All right, that's some intuition. Okay, it doesn't actually have to do that. It could leave it alone, but you can assume it moves itself because you can use pay again. Yeah. Okay, that's fair. I'm arguing with myself. That's fair. Okay, sorry. Because it doesn't have to. Like, it's not forced to move it, but up to a factor of 2, you can move it and move it back. Like we're willing to lose factor of 2 anyway. So So if you think of it as actually always taking some past solution and moving it to the current one, then if it was really far in the past, it moved forward a lot in time. So most of the time, you're using a fairly recent solution. Turns out that's not quite enough to get a polynomial in K So one more idea. If you think about what's happening, if you, let's say we use, I don't know, 1 over I squared, or some fraction of time using the solution. Okay, so let's get back to this. That's 2 minus I. So the proposal here is spend more time on the recent solutions and less time on the ones farther away. So if you think of these as balls growing, the one for the most recent solution is growing fastest, and the second most recent solution is growing a little bit more slowly, and then more slowly, more slowly. The old ones are still growing, but they're growing very slowly. Okay, so one thing is when one of these balls eats up another ball, you can stop the one that got eaten up. It's never going to be useful, and you can then stop growing, and then that'll allow you to re-normalize things so that older solutions get kind of moved closer in time. If you do that, then that does it. So that gives you this polynomial approximation. Final result you get out of this is either k to the 4th or k cubed, depending on your exact model for counting costs. Roughly, the question is how expensive is it to figure out things like, has one ball eaten up another ball? How much time should I be spending? These sort of things. So just figuring that out requires solving for these distances. Do you count that or do you not count that? We know how to improve it to k squared if we only care about the specific k, so much else is k. We can just care about that one using a different algorithm. The best lower bound we know is k, because you just get that because you don't have any feature information to get below that. You need to use feature information, but that's the weird thing. Okay. So more broadly, this was just one kind of tangent algorithm design using past instances to determine when it starts. More generally, this area considers families of algorithms defined by various parameters. In this case, the family is defined by the initialization. So if you have an algorithm, the parameter is where you start it from. It's a multi-dimensional parameter, maybe, because where you start it from is a bunch of different parts to it that defines the family. But other kinds of algorithms behave differently. And then kind of the question posed here is, can the approximation algorithm's perspective give us provably efficient ways to find near-optimal algorithms in this family, possibly given access to natural ERM oracles or other things, or do nearly as well as the best one. So that's it. Questions? Yeah.
I feel like solution that mediates this problem, or like you mentioned that it's like has it's determined right? So that's each solution on the graph. Sure, no.
Let's see. So as an example, we can think of like network flow kind of problems or something like that. Then these would be each instance would be a different graph, maybe on the same nodes or something like that, same size, but nodes, different edge capacities and so forth. We need to solve, or maybe some matching problem. We need to match up, resources and people. And so your algorithm is going to start maybe so you solved already for a flow in the previous graph, or you solved for a matching in the previous thing. Now the new graph comes along, these edges don't exist anymore, but you can still start from there. And then you just need to update it. So that's the way maybe to think about it. So it's just you had to, every day you have to match up, people to projects, whatever it is. You have the previous solution, students to what grant they're being. Whatever kind of thing it is, I think of something that we do every so often, and then you start from that solution, and then you try to update that. So that's it.
Okay. So I think everyone is.